Okay, let's take a look at this one. Consider the quasi-static expansion. So quasi-static means, remember that we're going super duper slow, so there's no explosive ideal gases. Sorry, ideal gases can explode. This is not one of them. Oh, by the way, you know what really upsets me? This is the plural of gas. That is clearly pronounced gases. This plural of gas should be this, and people are stupid. So I'm just letting you know that I'm forever going to spell this plural of gases correctly and not how the rest of the world thinks it should be spelled. Anyway, consider the quasi-static expansion of an ideal gas between the equilibrium state of figure A and C, or 8 and C. Anyway, blurb, 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 blurb. Where did it go? A to C. Okay, here's A. Come here, A and C. C. A to C. Okay, if it's going to traverse the path A, B, C, how much heat is required? Assume that P1 is 2100 or 210,000 Newton meter squared. Oops, that's this one down here. And P2 is 105,000. V1 is 225, but then it goes 1, 2, 3. And this one also goes 0.0045. Okay. And then the question is, I've got to get my stupid calculator out, and I don't want to right now. I'm going to do it on my phone. Y'all just have to believe me. Or I could just trust that the math works. Okay, so I need to find the equilibrium state. So I'm going this way, so it's going to be a positive number. Basically, I just need to know what's the area under this curve. And since it's all up here, basically I just need, well, the area of this giant rectangle. I don't know why this is not complicated. What is this distance here? 0.0045 minus 0.00225. Oh, look, I can do a 9 or a 4 here and a like that. Look. Look at me doing things like nobody's business. I think I'm doing this wrong. Okay. So the width of this is 0.00225, and the height of this is 210,000. So I just need to multiply that together so I can find the area under this curve. Let's do that on my phone right quick, except okay, my phone is almost dead. I gotta do my Duolingo. 210, and then 0.00225 times. Oh, apparently I did the math wrong. Okay. 0.0045, 0.00225. Oh, I missed an O. How did I miss an O? Let me try this again. 0045, 0.00225, 0.00225, and then times 210, dum dum dum. I got 472.5. Oh wait, that is what I got. 472.5. That's what they got. I'm just being silly. Okay, so the work done under the path is 473. Okay, so the work done is this number here. So the work done is 210,000 times 0.00225, and that equals 4, come here girl, 472.5 joules, right? Because this is newtons per meters squared, and this is cubic meters. So this goes away, this cancels out, and I get Newton meters, which is the same thing as joules. Okay, so the work done by the gas is 472.5. So that tells me the work is done. Okay, how much heat is required? So if 515 of heat is added to the gas as it traverses that path. Okay, now I need to find the work done along ADC. Okay, so I'm going to erase my picture. Okay, so ADC, oh, well, that's basically the same thing. It's the 0.00225, but now it's just 105,000. So I'm really just finding this area here. So ADC is, I know the answer's right here, but I'm just like to write it. 105,000 times 0.00225. So I've got 105,000 0.00225, 236.25. Okay, so that's how much work it takes to go along a DC. Okay, so we know that 515 heat is required along ABC. So 515 heat, this is the heat, is how much is added to do the ABC. Okay, and that's also the same one. And then it also takes 273 work. So ABC takes heat and requires 473 work. I'm going to make this smaller so I don't have to keep doing that, even though it's a little annoying. Okay, so 473 work. Now, the ADC side, we don't know how much heat that takes. That's what we're trying to find. But we know that it takes 236 work. We don't know the heat. But since they're both starting at A and going to C, that means that they have to be equal. Does that make sense? Okay. So, again, since we're both of them are starting at A and ending up at C, whatever's going on at the end of the day, since we start at A and end at C, we have to end up with the same picture. So we're able to find the heat to the work, or we're given the heat for the first one. But since we can find the work using the graph for each of the two different paths. So remember, whenever you're doing the work for ABC, it's not just the area of the square, it's the area entirely under the curve. So it's going all the way down to the axis. Okay, so it's not just this part. It's not just that area, it's the area all the way down. And that should make sense because whenever you're doing the ADC part, it's just this area down here. Okay, so the 515 minus the 473. I'm going to lose a little bit of precision here because I'm doing this on my phone instead of my real calculator. 236 plus. So Q is about 278 joules. So that's about how much heat is added to the system whenever I go that way, which is less heat, but it also requires less work. So that's pretty cool. So very, very, very basic use of first law of thermodynamics. We are, again, not trying to do anything super crazy here. We're just trying to have a little bit of knowledge, not even that we're necessarily going to remember it past 2 weeks from now when you take your final exam. It's just mostly so that eventually, whenever you go take chemistry, if you haven't had it already, Or eventually when you do take thermodynamics, that whenever you go take that class, you're like, oh yeah, I feel like at some point someone tried to teach me this. Okay, I guess I'll go learn it this time. That's the dream. All right, guys, you got this.